Welcome, everyone. It's my absolute pleasure to introduce Professor Jean Dragona, an associate research professor in the Department of Civil and Systems Engineering and Johns Hopkins University, and a member of the Ralph S. O'Connor Sustainable Energy Institute. Professor Dragona is a leader in advancing scientific machine learning, constraint optimization, and model-based optimal control, with a particular focus on energy systems optimization and building control. Today, Professor Dragona will present his exciting work on Neuromancer, which is an open source library designed to bridge the gap between machine learning and scientific computing. Written in PyTorch, Neuromancer offers powerful tools for solving parametric constraint optimization problems, physics-informed system identification, and model-based control, all while embedding prior knowledge in physics. Uh, so Professor Dragona's work in developing Neuromancer exemplifies his commitment to creating cutting-edge solutions for real-world problems. Please join me in warmly welcoming Professor Dragona as he takes us on this journey. It's all yours, Professor.
Thank you very much, Soprano, for the introduction and for the invitation. I'm going to share my screen, and I will first start with slides that can provide high-level overview of the underlying methodologies behind the Neuromancer library, and then I will have a couple of coding examples in Google Colabs. I have this 2-hour invitation in my calendar. Do we have full 2 hours, or what is the timeline for the presentation and discussion?
We have full 2 hours.
Okay, so we can really make it interactive. So you're not bored listening to me for 2 hours, so it will be too long. If there is any confusion or you have any questions, just interrupt me anytime, and we can either derail to specific topics or do some clarifications. So the work on Neuromancer started when I joined the Pacific Northwest National Lab almost 6 years ago, and it has been developed there with my wonderful colleagues, mostly through funding through Department of Energy, with motivation to deal with optimization and control of complex energy systems. And this is a challenging area of interest because we are talking about heterogeneous systems from buildings, power systems, transportation, wind technology, and energy storage that are governed by different physical principles and are typically modeled by high fidelity simulation capabilities. That's what they have in common. But these high fidelity simulation models are not directly suitable for real-time closed loop decision making and control. So there is a need to come up with more computationally tractable simulations without sacrificing fidelity of these models too much. So there are several challenges when it comes to modeling of these systems, where when we are talking about high fidelity models, we are typically talking about so-called white box models, where we are building component-based models from first principles, where each of the components represents some subsystem. And very common modeling tools are MATLAB Simulink or Modelica language that allow us to do these high fidelity white box models. There are a lot of custom models written in C, C++, like legacy codes for specific simulations in power systems or energy systems. But they are good for emulating the system, for studying the response of the system and its complex behavior. They are not suitable for decision making. So for those purposes, we typically resort to gray box models and black box models. But we are using different tools and theories for those that are not directly compatible and integrated necessarily with white box models. And when we solve these decision-making problems, we are having two categories in general. One is engineering approach, where we know all the models, we know all the equations that are representing our objective functions and constraints, and we typically solve some sort of optimization problem, whether it is optimal design or optimal control, where we are searching for some decisions, what we call primal decisions, um, to satisfy given equality and inequality constraints and minimize certain performance function. And this can be minimize energy use in buildings while satisfying operational constraints and comfort constraints on temperatures, or this can be minimize the cost of energy generation by satisfying the power system constraints. All of these methods are typically solved with some sort of constraint optimization solvers like interior point or active set methods. There is historically not a lot of learning in representing these functions. So everything comes from engineering. And similarly, when we are dealing with forward simulation of models, we have the right-hand side of the differential equations written, and we have the numerical solvers developed as a fixed set of rules. And we can study heat transfer through structures or structural stability of systems. These involve solving differential equations. On the other hand, when there is no physics, there is just data, especially labeled set of data set of some features, which are independent variables, and some outputs, which are the dependent variables. We are building some data-driven supervised machine learning model. And this can be as simple as linear and polynomial models, but these days everyone is using deep neural networks for most of the supervised learning because of their superior performance and very user-friendly software ecosystems. For decision-making schemes, where we cannot represent our system models in differential equations or as a constraint optimization problems, but we have some digital environment, or at least we can interact with the real system on a sampling basis, then reinforcement learning is a very powerful methodology that allows us to learn the fitness function of the controller that is co-created and optimize the actor, the control policy, to control the desired system to steer different reward functions or reward signals. So these are two historically separate communities, engineering and computer science, that approach these problems from different angles. But what we see today is more and more interactions. So some physics is being used in learning, and some learning is being used in engineering. But it's not as easy from the engineering perspective, because the historical separation of domains also created the separation of software tools. So when you are coming from operational research or control community, you are probably familiar with constraint optimization modeling libraries like PyOmo or CVXPy, Gecko, that have Python interface, Jump, which is modeling language for optimization, Julia, or more control-oriented like Casadi, that basically provide you with interface for high-level formulations of optimization and optimal control problems that can be automatically translated to solver-specific formulations. And this was very tedious manual labor 20 years ago. Today, it's automated through these algebraic modeling languages that allow you to utilize high-performance solvers like Gurobi or Cplex to solve these constraint optimization problems. Similarly, in differential equation space, you have a lot of commercial solvers or open source solvers, in especially in Python and Julia, for solving initial value problems and boundary value problems of differential equations. But historically, all of these tools require knowledge of your constraints and knowledge of the differential equations. While in traditional machine learning approaches like PyTorch and TensorFlow really revolutionized access to state-of-the-art machine learning for broader engineering and scientific community. So you can see in every single domain these days, any grad student can learn deep neural network and provides like state-of-the-art performance on a range of applications. And that's what really is the revolution in science in the last decade, the accessibility of these machine learning tools. But what we see more recently is that pure black box approaches have limitations. You need to have large number of labeled data sets, and it's very hard to satisfy physical constraints that are necessary for safety critical systems that are often present in critical infrastructure. So the potential answer to resolve these issues is so-called scientific machine learning that systematically integrates machine learning methods with mathematical models and algorithms from traditional engineering domains. And we are talking about integrating algebraic constraints in machine learning models, or integrating differential equation solvers in machine learning models. So a lot of different flavors of basically bridging the barriers between process-based models and data-driven models in one coherent algorithmic framework. And as I mentioned, like, why would like to do that? Because very often we want to have some performance and safety guarantees on our systems, and other time we have only small data sets, so we want to impose some kind of inductive biases towards learning physical systems. An example could be in energy systems in buildings. We want to learn thermodynamics, the heat transfer to the building structures, and how it interacts with the outdoor environment and its heating, ventilation, air conditioning system. And this is high dimensional system. If we are about to learn this purely from data, we would need to have thousands or hundreds of thousands of data points, which would often mean that we need to have years of training data, which is not that common. But when we know the physics, like we know that this is thermodynamical system that is reaching its equilibrium, is thermodynamically stable system, we can impose those physical constraints on the machine learning model to reduce its data requirements, because we are reducing the degrees of freedom in the model. And this allows us to reduce the amount of data from years to, let's say, to months or to weeks. So it's very often a very important requirement in real engineering applications where we just don't have that much data. And how it is enabled is through automatic differentiation, which is nothing else, just backpropagation algorithm that is used for training deep neural networks at scale for not only deep neural network architectures, but arbitrary computational graphs that can involve computational nodes, not only in the black box components, but these engineering-based models. So for further details, I really encourage you to go and search for some literature reviews. For instance, this physics information learning from Nature is a very good one to start if you are not familiar with scientific or physics-informed machine learning. To give you very biased and incomplete literature review, I'm just listing a couple of papers that influenced my thinking in this area. Differentiable programming system to bridge machine learning and scientific computing from the Julia community is a very good start for really the foundational vision behind gradient-based optimization and its use to design, optimize engineering systems. Learning to solve through physics-informed neural networks is a very famous paper that I will go over also in examples that allows us to solve partial differential equations. Learning to optimize are methods for integrating constraint optimization solvers in deep learning to satisfy all sorts of constraints that are occurring in operation research applications. Learning to model with neural operators is basically system identification. How do we learn surrogate models of dynamic system given some time series data? And learning to control are also interesting applications of using differentiable models to guide the policy optimization. So you can think of this as integration of optimization-based approaches for control, like model priority control with reinforcement learning. So when you look at all of these different modalities in scientific machine learning ecosystem, you may abstract four basic components of any scientific machine learning methodology. And the first component is some sort of active sampling or data acquisition, whether it is sampling collocation points in parametric space or hypercube sampling, or it's excitation of the system to obtain some time series model or response of the system to a signal. They really are very important in providing the input information for the machine learning model or some surrogate architecture that will map this data in the solution of the physical problem that incorporates some sort of domain prior. This can be partial differential equation as a layer in the architecture, or it can be some inequality constraints or other form of dynamical system representation, like state space model, that provide inductive biases or specific structural components that help to solve task at hand. And the last component of the SciML model is domain-aware or physics-informed loss function, where you add additional constraint penalties or additional regularizations on the physical properties and constraints. So again, there's a lot of literature that provides overviews and tutorials on the scientific machine learning methods. So I encourage you to go over some of those references in your free time. But I will start with PINS as probably the most famous example of scientific machine learning methodology that allows us these days to solve large-scale partial differential equations by pre-training the solution as a neural network. So instead of solving this with finite volume, finite element methods, we are going to use neural network to replace the solver. This allows us to have basically continuous solutions. We are not required to have any meshing strategies, and because it's pre-trained, it allows for typically orders of magnitude acceleration at the inference time. This is very important from the perspective of some parametric studies when you want to evaluate a large number of scenarios. So these are examples from NVIDIA models, that state-of-the-art PINS library, that are showing some examples of partial differential equation solutions compared to the numerical solver. So with your naked eye, you cannot even see the difference. And yeah, the state-of-the-art tools can really approximate the numerical solvers into sufficient accuracy. How they do that is in the vanilla approach, like the original paper, is very simple. You are sampling collocation points in your partial differential equation domain, which are typically some spatial and temporal coordinates. So here I have two-dimensional domain, one temporal, one spatial coordinate, and these blue dots represent the space, the points in the space-time that are essentially features for my neural network approximation of the partial differential equation solution. So I'm mapping the space and time into the PD solution. And this PD solution is evaluated in the known partial differential equation. So for that, I need to have these partial derivatives of the solution with respect to time and spatial coordinates. This can be effectively computed with automatic differentiation, whether using PyTorch or some Julia libraries. They can really do it with ease and few lines of code. And what you end up with is that domain layer, that PD equation that has known physical structure. And you know that this is equality constraints essentially. So in the loss function, your first term will be minimizing these equality constraints towards zero, because as this residual of the equality constraints limitly converges towards zero, it means your physics is being satisfied. And how you do that? Well, you are typically penalizing some absolute error or mean squared error of this equation over the sampled scenarios in your collocation point. So this NF is number of blue points in the domain. So it's some kind of weighted average performance. Additionally, you can add constraints like boundary conditions, which are typically supervised signals, where you are trying to minimize the residual of your neural network solution from some supervisory signal. So this is a standard loss function in deep learning. And then you basically add them together, maybe some weighting terms. And there are way more additional regularizations and way more advanced techniques, how to do the domain decomposition, how to do smart sampling in this PD domain, what type of architectures you use here, whether it is multi-layer perceptron or Kolmogorov-Ardor network. A lot of research is being done these days into different representations that are either more data efficient or converge better. So that's PINs in a nutshell. Very popular and very active area of research, as a number of papers on this topic demonstrate, which allows you to learn neural network solutions to known partial differential equations, or if you have data and unknown parameters in the PDE, you can also do the inverse modeling. You can estimate the parameters from the data given the known partial differential equation. So that's PINs. Any question on this one at this point? If not, I will go for learning to optimize, which is method actively being developed and researched mostly by operation research community. And I would argue it's very conceptually similar to PINs. Where it is being applied is mostly in operation research application areas like power systems or optimizing the logistic networks or optimal control of energy systems. And here the idea is that you want to take neural network that generates solutions to typically large-scale optimization problems that are subject to some constraints that you really care about satisfying. In PINs, the constraint satisfaction is a soft constraint penalty. If you violate it slightly, nothing horrible happens other than loss of accuracy. But here, the violating of the constraints can lead to catastrophic failures. So there is a lot of research on so-called feasibility restoration layers. How do we satisfy that the neural network generates solution in some feasible domain? So here is the graphical representation of how this neural network can generate solution of such so-called parametric programs, where each frame represents new instance of the optimization problem. That here the feasible domain is this half donut shape, and it keeps shifting in space and expanding, and objective function, which is that performance criteria, is also changing slightly. So you can see that there is a functional dependency of the optimal solutions to this problem with respect to changes in the parameters of this optimization problem. And that's what this learning to optimize approach is trying to find, the mapping between these parameters and the optimal solutions, which is not easy problem, because we are typically talking about really high dimensional problems in thousands or hundreds of thousands of decision variables. And here I'm just visualizing academic example in 2 dimensions. So how it is being done technically is very similar than PINs. We are typically sampling the parametric space of the optimization problem. And in this case, I have some 2-dimensional parametric space. And those parameters are represented by this vector xi. And I want to find the mapping of the xi to decision variables x with the neural network. So that would be this expression that satisfies some given constraints and some given parametric objective. And I want to find the weights and biases of this neural network that find this mapping. In the vanilla approach, like you would do in PINs, I will just minimize the weighted average of the objective functions over given samples and minimize the violations of these constraints via constraint penalties. So this is exactly how you would do in PINs. And then I would obtain some approximate solution of this neural network. But there is no guarantee that this will be feasible. So a lot of effort is put into those domain-aware layers that will satisfy feasibility guarantees, and they are often called feasibility restoration layers or repair layers, or technically how they are being implemented through some differentiable optimization solvers. And then they can represent very simple algebraic manipulations for simple constraints like box constraints, or some iterative solvers like projections or other proximal type operators, or they can even represent whole optimization algorithms like some quadratic programming solver that you can differentiate through implicit function theorem. They get more and more technical, more and more complicated this correction layer becomes. But we'll go through some examples today, hopefully, if we have time to demonstrate some of those more simpler approaches. So you can think of learning to optimize as a pin-like approach for constraint optimization problems that is really focusing on how do we satisfy the feasibility, because that's very important in many of these safety critical applications. Another category of scientific machine learning methods that has increasing popularity is learning to model for dynamical systems, especially with using so-called neural operators. And here is an example of like state-of-the-art capabilities by NVIDIA by using ForecastNet, which is based on Fourier neural operator that incorporates prior physics, the Fourier decomposition, the meshing of the grid of the weather forecast to provide long-term climate modeling. So more and more approaches are being used where typically only physics-based approaches being done with tremendous amount of engineering effort. So the idea is, again, how can we accelerate the modeling of complex physical systems that are changing in space and time? And there are different approaches like neural differential equations or these neural operators or universal differential equations that combine some sort of domain knowledge with some function approximator. So here is a simple schematics of neural network representing the differential equation model that is integrated in ordinary differential equation solver. So that's more technically how are we actually doing that? Well, the architecture is, you can think of as a black box or gray box representation that has some neural network component, and we are using our solver as a layer. So this is the famous paper about neural ordinary differential equations that showed how using standard tools in numerical methods, like the adjoint equations, allows us to backpropagate the gradients through these solvers efficiently. So how do we typically train these is that instead of some sampling of the parametric space, we are having time series data that represents observations of our system states. And if it's unknown autonomous system, which means there are some control inputs, we also have time series of the control perturbations and then the state response of the system to the control perturbation. And how are we training them? It's typically some sort of finite horizon rollout where we are minimizing the prediction of the model from the observed trajectories. If the trajectories are not noisy, you can minimize finite differences and have additional regularizations on stability or different weights of the prediction. So you can have like the weight decay and put emphasis on the first couple of time steps and then gradually decay as you go into the future. So there is a lot of different variations of what type of loss functions you can do, and also a lot of different variations of what type of these neural operators you can do. Example, besides neural differential equations, is this Koopman operator that is based on Koopman theory that says that every nonlinear dynamic system can be represented as an infinite dimensional linear system, given you find that appropriate coordinate transformation from the nonlinear to linear. And very often this is a hard task, so people can do it either manually as some candidate functions that can be polynomials or some trigonometric functions, or you can learn them from data as neural network representations that will map your observables into the latent space, and in latent space you will have this linear system dynamics representation that you can simulate forward in time and then project back into the observable space. So it's also very popular approach besides differential equations in dynamic systems and controls community with very active research topics. So that's for learning the dynamic system representation. The next question is, can we learn how to govern or control dynamic system representations given data-driven models or some physics-based models? So if you know some system, you want to find neural policy that governs the system, and you can do it in very similar fashion like in a system identification. So the concept is similar, again, end-to-end differentiable engine that starts with some sampling of the control parameters to optimize neural control policy, and the domain prior is the system dynamics model. So in the literature, you can call it the differential control. It's very often called, and this allows you to learn stabilizing policies for systems that are unstable, or do trajectory tracking, or some trajectory optimization for dynamical systems. And how you do it technically is, again, you're sampling the control parameters that can be initial conditions or different goal parameterizations. And then you are propagating those parameters, those xi and initial conditions, through some neural network control policy that generates control actions that perturb the system dynamics that can be either learned previously from time series data in system identification or given as a physical equations of the system. And then you perform open loop rollout for some fixed horizon, evaluate different constraint penalties, and use these pin-like loss functions to, again, provide the gradient for this policy. So it's different approach than reinforcement learning that would require learning the critic function by interacting with the system. Here, the critic is given by the system dynamics and the constraints and the parametric objective functions that are known from control theory and dynamic system. So these are the four modalities of scientific machine learning methodologies that we supported and implemented in Neuromancer scientific machine learning library. So now I will have some time to go over code examples for all of these four methodologies. So the general concept of the code is that we want to provide quick prototyping environment that allow you to go from high-level mathematical formulations of the constraint optimization or optimal control problem that has some objectives, some constraints, and some machine learning model to optimize those, into few lines of code that is based on abstractions known in operational research and controls community, where we typically build these problems based on the variable definition that defines the decision variables or problem parameters, on top of which we can write our objectives and constraints. And then we integrate it with machine learning architectures that are allowed in PyTorch and construct the constraint optimization problem. In few lines of code, these are the abstractions that basically under the hood generate the computational graph that represents your scientific machine learning model. You can think of it as a custom neural network architecture that incorporates all of these four components of the scientific machine learning model, which I was describing, which is the data set, the neural architecture, the domain priors or objectives and constraints that constitute loss function term. And the idea is to have few lines of code from the abstract problem formulation to some visualization of your results or some numerical analysis of the performance of your problem. Good. So I will go now to the library. Are there any questions at this point? I went through these scientific machine learning methods very, very fast, just to provide quick conceptual overview. And now I will go show some examples.
I think we have a question.
Yes, let's do the question before I go.
Yes, I have one question. So when you talk about learning for control, you assume that the system is like in a PDE format, but how about if the system is a autoregressive system that the states are not fully observable? And when it is not fully observable and autoregressive, how does that sampling process can be done? Like ideally, you have a space for a state, another space for a temporal. But if it is autoregressive, then these two are actually coupled together. You cannot actually perform like a random sampling or low discrepancy sampling. You kind of have to design the trajectory. Have you faced this kind of problem before, and how did you address that?
This is a very good question, and it's more like advanced topic in the modeling. I don't have the example here. We have some discussion regarding that in the library. I don't know whether I will be able to find it right now. For instance, his neuro-ODs with non-uniform time intervals can provide you with some information how to do that technically. So instead of initial conditions, you will have a time series that will initialize your autoregressive model. That's possible to implement, and we have some internal examples that are working well, but since it's advanced topic, we don't have it in open source examples. So regarding the partial observability, this is a very tricky question. If you have partial observable system, but all your controlled variables are in your observable space, it's not a big enough issue. You will come up with some kind of surrogate model that will map your observables to the next state, and because you are controlling only observable states, then you assume that the model, the input-output system that you are choosing is implicitly capturing those unobserved states. But if you have problem where you want to control those states which are not observed, you need to come up with some sort of state estimation.
Yes.
And it can be black box function that will map observables into those states that are not observed, like we do in this Koopman operator approach. And those can be physics-based, and those mappings don't need to be black box necessarily. You can add prior knowledge there. We exploited this in power systems modeling, and we have been even able to enforce certain properties in that unobserved latent states like stability, because we knew the steady states from the physical principles. But each applications will allow you to like apply different approaches. There is no like one approach to go. More involved would be to actually even employ Kalman filter or even optimization-based estimation, like moving horizon estimation in the pipeline. So these are all things that are possible. Engineering-wise, quite involved. But we want to provide ecosystem of abstractions that allow you to build these type of architectures.
I see. Thank you so much.
Yes, thank you for the questions. It was really, really insightful question. So maybe I start with quickly going over pins as an example that is probably most well known. And I would just go over the abstractions. I will not run the code because pins are quite computationally demanding, so it will take a while to train them with sufficient accuracy. But again, the idea is to take the neural network that maps spatial temporal coordinates in the solution of the PDE, and then you're imposing those PDE constraints and initial boundary conditions in the loss function. So how do we do that? First, we assume that we know the partial differential equation. Here, I'm going to do this diffusion equation. Just 1D textbook equation. I know the initial condition and I know the boundary conditions. So the ground truth solution looks something like this. Yeah, it's one spatial, one temporal coordinate, and this kind of wavy solution. So what I do, I first sample the data. I'm going to skip the code, just visualize this intuitively. Blue points are the collocation points, and the red points are the initial and boundary conditions. The blue points will serve as scenarios for penalizing violations of the PD constraints, and the red points will be supervisory signals for the initial and boundary conditions. So I'm constructing data sets. So we are building this as a dictionary data set, as opposed to tensor mappings that is common in machine learning pipelines. Why dictionary? Because we want to provide that symbolic abstraction layer on top of PyTorch. So there are tensor values and there are string keys that represent variable names. So I have X for spatial and T for temporal coordinate. That is my training data. And my test data, I have also the outputs, the labels of the PD for validation. And then what we are doing, we are creating data loaders. So if you are using PyTorch, you're familiar with data loader. It's a standard object for training deep neural networks. So instead of some tensor data set, we are providing a dictionary data set, and you can do all classical mini batching and shuffling of the data like you do in standard PyTorch training regimes. So that's the data generation, the first component of the SciML model. The next component is machine learning architecture. And here, this is a textbook example. I'm using toy problem. So I'm using also very simple multi-layer perceptron architecture that we have some of the architectures predefined in the blocks modules, but you can come up with your custom PyTorch NN module. Anything that works in PyTorch will work here because we are really providing only abstraction layer on top of PyTorch. So this is 2-layer TAN-H multi-layer perceptron with 32 neurons on each layer. And what we provide here with the node class is that symbolic wrapper. This works with any callable in Python, really, and it is based on positional arguments of this callable. So I know that this MLP, because we implemented as a star arc on forward, allows you to have multiple positional arguments. So I'm providing these 2 labels for input positional arguments, space and time, that will be mapped to the output of the neural network, which is the PD solution. So it's exactly this mapping. Space and time mapped to the PD solution. Okay, so I have data, I have neural architecture. The next is to define the domain layer, that pin layer. For that, I know the partial differential equation, and I need to have the partial derivative of y with respect to time and space. And basically that requires these partial derivatives of this neural network that can be obtained by automatic differentiation. Oops. Okay, everything else is just standard expression. So you could write it in PyTorch and write your custom class for that. What Neuromancer does for you, that you don't need to write any class, any function. You can write everything inline by using the variable expression. So I'm instantiating the variable given the input strings that basically represent as a keys. So you can think of it as a pointer, and it's a symbolic pointer in the computational graph. So this y hat, I know it will come from this neural network because that's what I told my node class to do. And this x and t is input to the node class, and before it came from the dictionary data set. So you can think of these variables as really the pointers to the data set and the neural network architecture. And now I'm going to build this domain-aware layer on top of these variables. That's like very common abstraction. Like you would do in CVXPy or Pyom or Jump. So now I'm using this grad method that calls automatic differentiation, autograd in PyTorch, and creates these symbolic derivatives. It basically automatically generates the forward pass that evaluates this grad function on these variables. So now you have these expressions that represent your symbolic derivatives that you can write in this partial differential equation and as this one line of code. And you can combine it with arbitrary PyTorch expressions. So it's very seamless integration in PyTorch with few lines of code. Yeah, so it is a PyTorch constant, PyTorch function, and this is these Neuromancer variables. And this will give you fpin, which is still new instantiated variable. You can evaluate it with the dictionary dataset, check the dimensions on its output. What is nice about the symbolic representation that you can change the shape of the dictionary of the tensors in the dictionary dataset, and don't need to change anything in the code. So, for instance, here I'm evaluating this as a batch with 1,200 samples. But I could evaluate it with single instance, and it would still work. Or I could change the batch to be 5,000 samples, and I wouldn't have to change anything in the code. We also provide these show methods on the variables that can visualize the computational graph. This is automatically generated, so it may not be the most readable, especially for more complex computational graphs, but it can help you when you are building this from smaller components and trying to have visualization to guide you with the common sense checks. So that's the third part, domain aware prior. Then the fourth part is physics informed loss function. So these are exactly the same equations that I had in my slide. So I want to minimize the violations of the PD constraints over a number of collocation points. Then I want to enforce the initial and boundary conditions as a supervisory signal over those number of collocation points on the initial and boundary conditions. And additionally, I may add additional constraints. Here I'm constraining the domain of the PD solution between minus and 1, because I know that this diffusion equation needs to lie in this domain. So all sorts of constraints additionally can be included. And how you implement that? Well, I provide here the scaling is not really important because all of the terms have equal scaling, but in practice you would really need to think carefully how do you balance numerically the different terms in this soft constraint loss function. But what we provide is the automatic constructors for physics informed loss function terms by operator overload on these comparator operators. So when I have equal sign, it means that I want to enforce this pin layer to be equal to 0. And it will broadcast over the distribution of parameters. Yes? Okay, so if there is no question, continue. That will instantiate this loss function term over here, LF. The LU, which is supervisory loss signal, well, I want to say that the output of the neural network over those samples and initial and boundary conditions needs to equal to the supervisory signal. And then I have these inequality constraints that my output needs to be bounded from upper and lower limits that are defined by this minus 1, 1. So again, few lines of code that gives you these 4 components of the loss function that can be put together in different ways. The simplest and most naive approach is use penalty methods. That's what I'm showing in here in equations. And that's why I show it in the code. But we have implemented also different approaches. You can use penalty barrier methods that also give you information about gradient in the interior of the feasible domain, or you can use augmented Lagrangian methods that have some update rules for dual variables that provide you with more information about constraints, or you can define your custom loss function aggregator, how you are basically combining these different objective terms and soft constraint terms to provide scalar valued gradient to be differentiated backward through the nodes. And here I have just that neural network, a single neural network that involves the pin loss function. So that's my constraint optimization problem. Yeah, so individual terms of constraints and objectives aggregated in some loss function, and everything's put together with neural network architectures through these node class abstractions in a differentiable problem. So now I have the problem, I can train it in the trainer class using the dictionary data loader and standard stochastic gradient descent. And you can add some hyperparameters like early stopping and what metric you want to use for training and validation, but that's like standard PyTorch thing. We also integrate with PyTorch Lightning, which has a little bit different syntax and provides you with better performance and data parallelization and multiple GPUs for really large scale training. We can go to that example if there is interest. But for the purposes of introduction to the library, this is probably the simplest example that allows you to train the neural network to solve this pin problem and then compare it with numerical solution. You can evaluate the residuals. So that's the typical workflow for physics info neural network. Are there any questions on this example? So I'm going to show you another example that is in learning to optimize space that is using the same principles than pins. And I'm going to run this so I can interact with this example. Again, as I mentioned, very similar approach than pins. We want to find the mapping between problem parameters and decision variables of constraint optimization problem. And we are going to do so by sampling these parameters, training the neural network based on the gradients from this constraint optimization problem. Restart section, I don't know. Yeah, so you don't need to install anything. You can just run these examples yourself. But first time when you run the example, you will probably obtain some error. So all you need to do is to just restart session and run again. And then the installation from pip install is working correctly. Let's do it again. Something is wrong here. Restart session. Yes. Wrong. Oh, this is very strange. Should have been working in the Google Colab. Let me try to run this again. I'm on a VPN, might be an issue, I don't know. Okay, it seems like I have some issues here with the runtime in real time. Okay, I'm not going to troubleshoot it right now. I'm just going to walk through the Google Colabs, but maybe if someone else can try to run and confirm that it's running on their end, so I can diagnose whether this is my local problem or we crashed our distribution on pip, which I think we shouldn't, but yeah, let me know if you can run this in your browser. So I'm going to show you example where we are solving this Rosenberg problem with this specific objective function that is non-convex and non-convex feasibility domain. I have two parameters, A and P, so they'll be shaping the objective function and constraints. And because they are two-dimensional, I can conveniently visualize them. So I'm sampling this parametric space, similarly like I'm sampling spatial temporal coordinates in the PDE. And then I'm mapping these coordinates into the primal decision. And again, using the same neural network like before, and using the same node class to make it symbolic abstraction, making these A and P parameters into primal decision variables. And then I'm instantiating the variables, and we can even do slicing on those variables that can provide us with more flexibility how we formulate the problem. So this will be my Rosenberg objective function, and I decide to minimize it to generate the objective function term. Then I'm having these inequality equality constraints. I can put some labels on them, so for visualization it will be nicer. And then I'm having list of constraints, list of objectives, and list of these trainable components that I'm aggregating in the penalty loss function and putting it all together in the problem. So the same abstraction that I use for things, I'm using for learning to optimize. Therefore, I can use the same PyTorch ecosystem of data set dictionaries, data loaders with this problem on the trainer using stochastic gradient descent. And after training, I'm able to solve this parametric constraint optimization problem as an approximation. So here is one instance where the green is coming from interior point solver and the red one is coming from this learning to optimize in Neuromancer. And what is the difference between those? That these learning to optimize problems can provide you with massive acceleration at the inference time because they are pre-trained over distributional problems. Their solution speedup factor can be orders of magnitude. In this case, it's 2,500 times faster, while retaining the solution quality compared to the interior point. So that's really the nutshell. Why are we doing these scientific machine learning surrogates? Because we want to accelerate this computation. Okay, you have same error in your browser. So I think we must have crashed our distribution on pip install. So that's something to troubleshoot. So I'm going to create the issue right after this meeting. Good. So is there any question on learning to optimize or pins and their similarities?
Hi, I have one question regarding actually for the learning to control
Mm-hmm.
that could you explain more like the difference between the learning to control with reinforcement learning?
Okay, let me go to example that will help me to do that. So in simple terms, reinforcement learning, especially actor-critic approaches, require you to learn the actor to generate control actions that will perturb some environment. And that environment you treat as a black box. It's something you are interacting with, and it will provide you with system measurements of states and reward signals. And for those, you are learning also value function, which is mapping your state action pairs into those rewards. And that's scalar valued fitness function that is telling you what is good, what is bad. And because you are approximating with neural network, you can compute gradients for the policy optimization, because you know the steepest descent on these value functions, you will find the extremum, the minimum in this function. Or in reinforcement learning, is the other way around. You want to find the maximum. By the same principle, it allows you to use the automatic differentiation for gradient-based optimization of the control policies. Here, the value function is replaced by known system dynamics models, known constraints, and known objective function terms. So the example would be as follows. You have the system model. So this is the differential equation that represents this two-tank system. It's one of the canonical examples in control theory. It's nonlinear differential equations. Don't need to worry much about its interpretation. Is very simple, but you have like two control actions. So one is pump modulation and one is valve opening, and you want to control the levels in the tank. And the conceptual diagram is as follows. So you have the control policy, which is your actor. And in reinforcement learning, you would have critic, and then you would interact with the system. Here we have some internal model of that system. That's the differential equation. And we are not going to train it with gradients of the critic. We are going to train it with the gradients of the known expressions of our reward function. So mathematically, you can represent it as a parametric optimal control problem, where your reward is like reference tracking or terminal penalty and additional constraints penalties over some finite horizon rollout, which is averaged over some distribution of the scenarios you want to optimize it over, which will be initial conditions or different goal parameterizations. And really the trick is here, or like the difference between RL, that you have some system representation. In this case, this the differential equation that can be neural differential equation, a Y-box differential equation, or some state space model.
Yes. Yeah.
Yeah.
Thank you. That's answering my question. Yeah.
Yeah, perfect. So how is it related to pins? Well, we are starting with sampling of this parametric space. So here it would be the initial conditions or different like goal parameterizations. And I'm using the same dictionary data set for my initial conditions and desired references, and the same type PyTorch data loaders. So that would be the data generation part of the SciML model. Now the machine learning part of the SciML model will be the neural network control policy that will be wrapped into these nodes. So it will be mapping initial condition states and references into control action. So that will be this multi-layer perceptron. And this is modification that has some bounds and constraints. Then I have the domain prior, which will be the system model. And that will be this white box ordinary differential equation, where I assume that I know the parameters. If you don't know the parameters, you could estimate them from data with system identification. There also works how to train the parameters simultaneously with control policy. Because this is a continuous time model, you need to have some sort of system solver integrator. This is Runge-Kutta fourth order that will solve this system. And then we are wrapping it in the node again, so it's symbolic. So it maps current states and control actions in the next states. And for that, we create this system that combines the policy and the dynamics model over future finite horizon end steps. So you can think of the system model as symbolic constructor of recurrent architectures over these symbolic wrappers. So that's really only for convenience, and system, this terminology from controls and systems engineering. So it can constitute of multiple nodes, and the interactions can have different topologies. So you can have multiple policies, multiple models. So you can, in principle, train multiple agents on multiple systems with single loss function. And how we do the loss functions in the same way how we did for learning to optimize and pins. We define some variables like states and desired references, define desired objective terms like tracking the reference, minimizing the violations of the constraints, maybe having some terminal penalty on the last state, so I can also do again slicing and indexing on the temporal dimension, because I know that in this particular example I will have 3-dimensional tensors. The first will be number of scenarios in the batch, the second will be length of the time series, and the last dimension will be the dimension of the state variable. And then I put again everything together in list of objectives and constraints, use the penalty, loss, and problem in the same way like I did in the previous examples. And again, the same stochastic gradient descent optimizer and same trainer that allows you to train these control problems. And you end up with neural networks that represent the parametric solution to optimization problems. So with each change in the initial conditions, you would obtain different trajectory tracking these references. So that's learning to control example. Yeah, that generates these control actions.
One more question. I guess it's gonna be a very basic question. Previously when I read your papers, I was a little bit confused by the naming that you call it as a differentiable predictive control. Is that still model predictive control, or is kind of
model predictive control is related but different methodology?
Yeah.
So model predictive control is one of the most successful advanced control methods that formulate the problem and minimize not the parameters of the control policy, but they minimize the finite horizon control actions. So these would be decision variables directly. So you wouldn't be searching for parametric representation of the control policy, but optimal sequence of the control actions given initial conditions and given trajectories. It's not sampling-based approach, which means that you need to solve this optimization problem every time you obtain new measurements of your initial conditions and desired references. So it's optimization approach, real-time optimization. The difference with this differentiable predictive control is that you're sampling the parametric space, you are learning this problem offline, and you're obtaining the parametric solution as a neural network, that at the inference time, you're executing neural network as opposed to optimization solver. Does this answer the question?
Yes.
Yeah. So it's inspired by model predictive control, but you can think of it as offline model predictive control.
Yeah, explicit model predictive control.
Exactly. Exactly. Explicit model predictive control.
Thank you.
Yes.
I have a question about the application of the differentiable predictive control. So is it possible to apply what you developed here to say C++ model? So like PyTorch, they have this LibTorch version that can be compiled together with some C++ based framework, simulation framework. But I'm not sure if the Neuromancer can have the similar capability.
So Neuromancer is built on top of PyTorch. So all the PyTorch code generation capabilities will work here, because everything what we implement is NN module, which is the basic abstractions for the neural network representation. So let's say here in blocks, everything is NN module.
I see.
Yeah. So, and that was conscious choice. So we don't limit the user in terms of the functionality. Everything what PyTorch enables is inherited directly, because we are only building symbolic abstraction layers on top of PyTorch. Of course, there may be some technical nuances when it comes to actual implementation and code generation in C. But yeah, that I haven't encountered. When we are talking about code generation of pre-trained models, that should be absolutely no problem. That should be very straightforward. But when we are talking about actually implementing training in C, that's different story.
I see.
Yeah.
I see. Yeah. Thank you. I think it would be great that we can load some pre-trained model into the C++. It will be great. Yeah, thank you.
Yes, and that's we don't have it in Neuromancer because this is basic functionality of PyTorch, and they have like extensive documentation for C++ API. So everything what they provide in their documentation is basically what you would need to do any code generation, because even here in this example, so what I end up with is this train model that is returned as an output of the trainer.train method, and this best model is NN module.
I see.
Yeah.
Yeah, I see.
Yeah.
So it can be converted to a JIT, so the JIT and
Yes.
it can be loaded in the C++.
Exactly. Yeah. And this problem, this penalty loss, the system node, this block, this integrator, this ODE system, everything is in PyTorch as NN module. Yeah, so you can really think of this whole framework as a custom neural architecture generator.
I see.
Yeah.
Thank you very much.
Yes, thank you for the questions. These are very important for any practical deployment. And since you asked about some of the applications that I'm particularly working with, and I work with my colleagues at National Labs, these are energy systems primarily, because I'm part of Ralph O'Connor System Energy. So building system, power systems, wind technology, energy storage and transportation networks are of interest. And some examples include learning to control building energy systems, where we know how to do model priority control. There are tons of papers how to do MPC or reinforcement learning. The problem is that they often take a lot of expertise, especially MPC, to design and deploy because of the modeling part. And in reinforcement learning part, it takes a lot of training data. So we want to come up with something that doesn't require a lot of expertise in modeling and doesn't require a lot of training data. And this differential priority control was specifically developed for these type of applications where the safety is not the primary requirement, but the cost of development and cost of maintenance of this control strategy is the primary concern, because no one is going to pay for army of PhDs to design advanced control method for every building. So here we are having some good progress in terms of accelerating these solutions and making them more user-friendly from the deployment perspective. So yes, I want to also maybe finish here. I think those examples are sufficient. We have way more examples in like maybe more advanced methods or also system identification, but I think they are good for like starting with the library. And I want to acknowledge all my wonderful colleagues at PNNL that contributed to the development of the library itself or to the associated papers on scientific machine learning and applications in energy systems. So thank you very much, everyone. And yeah, if you want to ask further questions, I see there is some chat. Yes, thank you very much, Negar, for showing up and staying with me for 2 hours.